Hello students, so in this lecture we will start discussions about magnetic relaxation. And resonance. Now there are numerous frequency dependent phenomena in magnetism. Uh, so frequency dependent phenomena involved in magnetism. And since it is impossible to deal with all of these, we have chosen paramagnetic relaxation. And nuclear magnetic resonance, NMR, as examples to illustrate the effect of this frequency dependent phenomena. And so we'll first start with the paramagnetic relaxation, this phenomena. Now, which we will be considering that there is an oscillating magnetic field. So let's consider there is an oscillating magnetic field present. Now, if we consider a paramagnetic material in the absence of an external field, then the magnetic dipoles are then oriented and random. So, paramagnetic material where the external magnetic field H is equal to 0. So, this will indicate that random orientation of the dipoles. Then the next stage is when magnetic field is applied. That means it is now not equal to 0. And so when the magnetic field will be applied, the random magnetic dipoles they will now start to get aligned according to the magnetic field applied. However, so there will be a net magnetization M. However, this value will reach a saturation, and with the saturated value when there is no more scope of the dipoles to get arranged according to the direction of the magnetic field, this saturation value is Me. So during the build-up of this magnetization, we can write the process in terms of this equation. You can write that the rate of change of magnetization is equal to saturation magnetization minus instantaneous magnetization divided by a term tau, and this is the relaxation time. it will, so this equation determines the rate of growth of the magnetization. So as we have told that we have considered an oscillating magnetic field. So uh, let's consider that magnetic field is given as H as a function of time is equal to He plus Ho cos omega t. So instead of this constant magnetic field, we are now supplying a oscillating magnetic field. So automatically the magnetization will be accordingly, that is m function of time will be equal to me corresponding to the constant magnetic field, plus the magnetization value will also oscillate corresponding to the frequency of the external magnetic field applied. However, this oscillation will have a little a phase difference, a phase lag, and it will be written as cos omega t minus phi. Write this one. Where phi is the phase lag. Now this is the phenomena which is called the paramagnetic relaxation. Now this constant field He, this constant field is applied parallel to the oscillating field, but it may also be perpendicular to it unless otherwise stated. We assume that H is parallel to the oscillating magnetic field. Now, if we introduce the term susceptibility, is M is equal to this term. So this equation will be written as M as a function of time is equal to I will use this term as psi s He plus we'll have two terms, one corresponding to Ho cos omega t and another corresponding to Ho sin omega t. So actually we have used this as we have cos A minus B. So cos A minus B is equal to cos A minus sin A. Now this is again the two susceptibilities, ratio of the two susceptibilities will be equal to tan of the phase lag, and for low frequencies the second part is equal to 0, and the first part is again equal to the susceptibility corresponding to the constant magnetic field, that is psi s. Now, so we can see that there is a variation of psi dash. It is frequency dependent, this value of susceptibility, and this is what is known as dispersion. This is dependence of frequency of the susceptibility. So this is so psi dash is the high frequency susceptibility, whereas psi double dash is the low frequency susceptibility, and the low frequency susceptibility on the other hand means psi double dash, the low frequency susceptibility, it is a quantity which determines the energy absorption. So determines absorption of energy by the specimen. And on further calculations, one can actually find the absorption per second per unit volume as equal to omega by 2 pi into integration of m d into h, and which is equal to omega by 2 into the low frequency susceptibility into h0 square. So you can see that the low frequency susceptibility is related to the energy absorption. Now, if we use the complex notation, which is a little more convenient, so we can write the oscillating magnetic field as equal to G plus H0 to the power I omega t. So the magnetization will follow the same path. It will be ME plus, we'll introduce another term, complex form of the susceptibility, into H0 to the power I omega t, where this complex form of susceptibility is star is equal to psi dash minus I psi double dash. So this is the high frequency susceptibility, this is the low frequency susceptibility, and this is the complex susceptibility. Now these two terms, that means psi dash and psi double dash. These two are again they are related to each other by a relationship called Kramer's chroniculation. So what we have learned that happens in the case of paramagnetic relaxation is number one is the quantities psi dash and psi chi double dash. They are related to the relaxation times, and the second notion is that the relaxation time must find an interpretation based on the properties of the magnetic atoms and the lattice in which they are incorporated. So it should be related to the magnetic atoms, that means the atoms and the lattice. So these two are the phenomenological twofold paramagnetic relaxation properties. Now let's concentrate on the relaxation mechanism. That it should be it is basically based upon two relaxation mechanisms have been proposed. The first one is the spin lattice relaxation. And the second one is spin relaxation. And this is large compared to uh, the internal magnetic field, and this one again is small compared to the internal magnetic field. So you can see that this is large and this is small compared to the internal magnetic field. Now let us go into the details what we actually mean by a spin lattice relaxation. So while discussing spin lattice relaxation, so let's start with spin lattice relaxation. So while discussing spin lattice relaxation, we'll assume that the magnetic interaction between spins is neglected. So we'll assume there is no spin involved. So this will isolate this phenomenon. So there is a divide relaxation equation which says that star is equal to S divided by 1 plus omega square tau square, and psi double dash is equal to zeta double dash is equal to psi S dash and omega t divided by the same denominator 1 plus omega star omega squared tau square. So the basis of this theory is that the relaxation time is associated with spin lattice relaxation is so long compared to spin relaxation that the spin system can be considered to be always in thermodynamic equilibrium. So this is considered to be thermodynamic equilibrium, and the spin system has its own specific heat, temperature, etc. Now the temperature Ts, consider there is a temperature Ts of the spin system is not necessarily the same as that of the lattice, may be seen as follows, because lattice are mainly related to temperature causing vibrations. So if we consider a spins of half, we consider a system of half spin in thermal equilibrium with the lattice, then we can say that what we have assumed, we are assuming that there is a spin system, spin half system, which is in thermal equilibrium with the lattice. So this is the case, then from Boltzmann statistics, we assume that the number of atoms which are parallel versus number of atoms which are antiparallel is equal to exponential 2 mu b Boltzmann atom h divided by the magnetic moment h divided by kt. This is a Boltzmann atom. So let's write it more clearly. NP by Na is equal to exponential 2 mu p h by kt. So this corresponds to NP corresponds to number of spins which are parallel, and this corresponds to number of spins which are antiparallel. Now in this case, if this is the external magnetic field applied, in this case if suddenly the field is from H, it is changed to H dash and increased, and whereas the temperature of the lattice is kept constant at T. So in that case, automatically this value, this ratio will get changed. However, it will take some time for the ratio for this NP by NA ratio to adjust itself to the new field. So it will take time. To adjust the new field. Now if we replace this H by H dash, so there we can define another temperature Ts such that the instantaneous population satisfies the Boltzmann's equation, and so this Ts is actually called the spin temperature. And so if H has been increased to H dash, T should be also increased to Ts. That means to maintain the ratio, so Ts is greater than T. Now, if the field is oscillating and we have a difference between the two, and the difference is say theta between T and Ts, Ts is Ts minus T. So this difference will also oscillate if we have an oscillating magnetic field. So as long as the difference is not too large, as long as theta is not too large, the heat transferred from the lattice to the spin system. So there is a heat since from Ts T. So this heat transfer occurs in a short duration of time dt. So we can write an equation given as dq is equal to minus alpha theta into dt. So this corresponds to the heat transfer dq, and this alpha is nothing but coefficient of heat contact. It's called the coefficient of heat contact between the spin system and the lattice. Between the spin system and the lattice. Now, the first law of thermodynamics for the spin system may be written as can write dq as equal to quantity Ch into rate of change of temperature with magnetization at a constant magnetic field plus Cm into rate of change of temperature with constant magnetic field applied, constant M into dH. So these two quantities, this Ch and Cm, they are specific heats at constant magnetic field and magnetization at constant H and M respectively. So we can write the difference between Ts and T as it is oscillating, as we have previously told. So theta can be written as equal to theta 0 to the power I omega t. Now if we use the relation dq is equal to minus alpha theta dt, so we can write this one as equal to minus alpha theta 0 is equal to, differentiate this, so it becomes I omega is outside, then CH into del T by del M at constant H into M0 plus Cm into del T by del H at constant M into H0. So we can write theta 0 is on the other hand is equal to del T by del M at constant H into M0 plus del T by del H at constant M into H0. That means what is inside the bracket, this one, if we leave aside CH and CM, only if you take only this quantity plus this quantity, it is giving you the theta 0 value. So we are adding specific heats as coefficients. So on further elimination, and what we get as the complex value of the susceptibility, that means chi star, and it is equal to the ratio MO divided by HO, and it is equal to del M by del H at constant temperature multiplied by the quantity 1 plus I omega by alpha into Cm plus 1 plus I omega by alpha into CH. And this is nothing but the static susceptibility psi s. So we can easily write the difference ratio, that means psi dash, the high frequency susceptibility, by psi s is equal to Cm by Ch plus 1 minus Cm by Ch divided by 1 plus omega square tau square, and the low frequency susceptibility ratio with the static susceptibility is equal to 1 minus Cm by Ch into omega tau divided by 1 plus omega square tau square. Now the relaxation time here is tau is simply equal to Ch by alpha, and it is determined by the coefficient of heat contact, that means alpha, and between the system and the lattice. Session time. So if we draw a plot between the ratio of the high frequency susceptibility versus with respect to the static susceptibility, with respect to the frequency, say omega whatever, so it will follow different plots based upon the magnetic field. So if the magnetic field is, say, A typical plot will be like this. Now, if we increase the value of magnetic field, this is H1, and for an enlarged, extended, for increased value of magnetic field, it will show value like this. So this is H2. So here H2 is greater than H1. And as we have said, this is the dispersion relation. This shows the dispersion, the high value, high frequency susceptibility, and the low frequency susceptibility is associated with adsorption or absorption. So in that case, if we take the ratio between the low frequency susceptibility and the static susceptibility with respect to frequency, this is the adsorption, the value A, energy absorption. So here, of course, the value will be a little different, the variation will be different. For low magnetic field, it will follow a plot like this. For high magnetic field, of course, the absorption will be higher, so it will follow a plot like this. So this is H1 and this is H2. So here H2 is greater than H1. So this is all about spin relaxation. Spin lattice relaxation. Next, if we consider the spin relaxation, so here the absorption associated with spin relaxation is associated with high frequencies. So we can say that we obtained here a high frequency absorption, and again written as A spin is equal to 1/2 omega square tau S by S Cm by Ch. So this value, interestingly, this is independent. This is a static value and it's independent of temperature. The relaxation time with respect to the static values of magnetic field and magnetization. So the typical values of some paramagnetic materials, like for example, if we take the material Fe, and there is a composite material NH4, SO4, 12H2. So this shows a static relaxation time of 1.1 into 10 to the power minus 10 seconds. Gadolinium sulfate, on the other hand, it has a paramagnetic relaxation time of 0.57 into 10 to the power minus 10 seconds. So this is 1 and 2. So we can see the values are very extremely low, minus 9 seconds, minus 10 seconds. if the dipoles are free spins, then the Larmor precision frequency, we can also write the Larmor frequency associated with, say, an instantaneous value of magnetic field Hi is omega L is equal to E by mc into Hi. So if this is the case, then the time required will be actually, or the time required for the spin to change its axis. Okay, the time required by the spin to change its axis, and that is in fact is the static relaxation time, and this will be almost equal to the inverse of the Larmor position. And so if we take the examples that we have just considered, that means if we take as for example FeNH4 SO4 to 12H2O. So it had previously shown that from experiments the value of relaxation time was 1.1 into 10 to the power minus 10 seconds, whereas from 1 by omega L consideration it is quite close, that is 1.2 10 to the power minus 10 seconds. Similarly, for the case of iridium sulfate, that is Gd2SO4 38H2O, the value of Ts experimental was 0.57 into 10 to the power minus 10 seconds, that is with respect to inverse of the Larmor position and frequency, it was 0.4 into 10 to the power minus 10 seconds. So it shows that it actually follows this relation 1 by omega L. So we'll take up NMR in our next class.